So good evening, everybody, and welcome to this very first PhD talk of 2024. Our speaker today is Andrea Manzoni. Andrea is a PhD candidate. He's actually at the very end of his PhD, and he's from the Environmental and Infrastructure Engineering program. He's working in MIPOR group under the supervision of Professors Monica Riva and Alberto Guadagnini. And today he will present basically all of his PhD. Let's hope in a reasonable time. His research deals with modeling flow and transport mechanisms in porous media in large-scale aquifer systems. So as usual, I remind you to fill this table, and with this I give the floor to Andrea.
Okay. So, thank you, Chiara, for your introduction, and thank you all of you to be here tonight for listening to my presentation. I'm going to talk to large-scale groundwater flow and transport model, some investigation that we have performed relying on machine learning. My work, as my presentation, is divided in three main steps, in three main phases. The first phase is going to be related to the geological reconstruction that we have performed for a large-scale domain powered by machine learning. The second is related to an inverse modeling methodology that we have developed in order to deal with large-scale groundwater flow model. And the last phase is going to be related to transport, to model transport using deep learning techniques. Specifically, we are going to see some application of convolutional neural network to transport within porous media, transport of contaminant. All the three phases are built combining physical-based model, physical knowledge, with artificial intelligence model. And of course, this data-driven model relies on a lot of data. This data comes from different sources. We have used data from remote sensing, from global scale model, from in situ sampling, and also we have generated some synthetic data for some application, like the third phase. Okay, let's start talking about the phase one. So the first phase is going to be related to the geological reconstruction, so the reconstruction of the distribution of geomaterial within the large-scale domain. This phase one is divided in three main steps. The first step is the creation of a data set that is going to be employed within the neural network model that is going to be able to build an hydrogeological reconstruction and also to allow us to quantify the uncertainty related to this hydrogeological reconstruction. The three main goals, or the three main objectives of this first phase are first realize and unifies data set with uniform data that includes all the data sources available in the large-scale domain. The second is to, of course, realize a distribution of geomaterial under the large-scale system for the study case. And the last objective is related to estimate the uncertainty associated to this reconstruction. Okay, let's talk about the study area. The study area that we have reconstructed is associated to the underground system of the Po Aquifer watershed. So we are talking about the Po watershed that is the largest aquifer in Italy, the largest watershed in Italy, and it's include also the area that we include also Milan, the Lombardy region. So we are actually inside the domain that we have reconstructed. And it embeds 1/3 of the population of the country, and it includes most of the industrial and agriculture activities in Italy. This area also includes a very intricate river network that further enhances the complexity of the system. Okay, let's talk about step one of phase one. So this step is related to the realization of a data set that includes all the data that are available, all the lithostratigraphic data that are available within the domain. In order to do that, we have combined three different data sets that are available within the area. These three data sets are associated with the three different regions embedded in the domain, so the Regione Lombardia, Regione Emilia-Romagna, and Regione Piemonte. And we have also integrated the national data set of ISPRA. So we have unified and categorized the data associated with this lithostratigraphic information. Here you can see a schematic example of a lithostratigraphic data that we have, all these points that you can see here in the map, each point of that is in the map corresponds to a well. A single well is composed by different layers that you can see represented here. Different colors in the well's layer represent different geomaterial, and this different geomaterial has been associated to a given layer, starting from the qualitative description of each layer that were available from the 3 different datasets. Each layer has been then divided in sub-layers of 1 meter depth. This is going to allow us to equally represent each layer within the training dataset that are going to be used in the machine learning. And after that, we transform the data into a cloud point data. This is due to the reason because the machine learning model work better with this kind of data. At the end, the dataset that we have realized includes more than 50,000 wells that lead to more than 2 million points that we have used to train the machine learning model that we have developed. So the model that we have selected is a multi-layer perceptron classifier. It's also called vanilla neural network. It's one of the simplest neural network that exists, but it's very suitable for this kind of application, like dealing with categorical variable, like in this case. Why we have decided to use a machine learning model instead of classical model, like variogram-based model? Even though we have a lot of data, more than 50,000 wells, these data are not homogeneously distributed within the domain. We have some area with very low density of data, and in these areas, the spatial correlation between points can be absent, so maybe it's not existing. And also think about how much data we have, and as everybody knows, this kind of data-driven model are really suitable for dealing with such a large amount of data. So that's why we have decided to use neural network. Okay, let's have a look on how this simple model works. We are not going to go into detail. We're going to I'm going to just introduce to you of this kind of model. This kind of model are made of 3 main components. The first component is the input layer. The input layer is here on the green box. Within the green box, it is composed by input nodes that are represented with these circles. Each input nodes correspond to 1 input variable. In our specific case, the 4 input variables are the position of the points. So we have x, y, z, and we also have the fourth nodes that is associated with the depth. Combining the depth with the z coordinate, the vertical coordinate, we are able to embedding the information of topography within the model as an input information of the model. The second component of the multi-layer perceptron classifier is the output layer. In the output layer, we have, in our case, 6 nodes that are associated with the 6 geological material categories that we have selected for our domain. Specifically, we have selected gravel, sand, silt, clay, impermeable rock, and permeable rock. Each of these nodes, after the processing, will receive a score, and in a given point, we're going to assign the geomaterial that is associated with the highest score. What is in the middle that goes from the input to the output are the hidden layers or hidden layer. How the hidden layer works? Basically, they take in input the information from the node from the right. And so in our case, in this example, they take the input's value. They perform just a weighted sum of this input, and they sum a bias. This sum is going to be passed through a non-linearized function. This is going to provide an output. If we have a single layer, single hidden layer, this output is going to be passed to the output, so we're going to have the score. Otherwise, it's going to be passed to a next layer. It will elaborate again this information until it goes to the output. So basically, here, what is to calibrate it during the training phase of the neural network are the weight and the bias for each node. Okay, now the question was, how many input layers and how many hidden layers and hidden nodes do we need for our problem? Which is the optimum value of these hidden layer and hidden nodes? In order to understand that, we have performed a so-called cross-validation to a different set of architecture, so a different combination of hidden layer and hidden node numbers. And so we have performed a stratified cross-validation. A cross-validation basically consists in dividing the entire data set into sub-data set and use one of these sub-data set to perform validation, while all the rest is going to be used for the training. You can see here yellow. Then we change the sub-data set for validation, and we use the other for the training. We repeat that until we use all the subset of data to perform validation. In this way, we're going to be able to use all the data at least once for validation. We have performed stratified cross-validation. Why stratified? Because, as already told you, the data is not homogeneously distributed within the domain. So we want that each sub data set will equally represent the information also in the area with low density. So what we have done here, we have divided, as you can see here on the figure on the top right, we have divided our domain in sub area, and we have imposed that all these areas were equally represented within the sub data set, within each sub data set that is using the cross-validation. In this way, we have compared the accuracy and the computational cost of 48 different architectures. So we have tested a number of layers that goes from 1 to 8, and a number of hidden nodes per layer that goes from 5 to 250 hidden nodes in terms of accuracy and computational cost. Here with a big red star represents the neural network that we have selected at the end, that has 7 hidden layers and 50 hidden nodes. And it was one of the neural networks that provide us one of the highest values of accuracy, but it was able to not have a very big computational cost. That's very relevant because we have decided to go with a probabilistic approach for the reconstruction, so we're going to need to perform a lot of training and a lot of reconstruction, and so we need also a limited computational cost for that. So after that, the neural network that we have selected is a little bit more complex than the simple example that we have here. Basically, we provide an input the coordinates of each point of a grid that we have constructed for our domain. And so in input, we will provide the x, y, z coordinate and depth of each cell of the domain, and the output of the model will be a single category in each point of the grid, the simulation grid. As I already told you, we have decided to go for a probabilistic approach. So we haven't performed a single training and realization. We leverage on the random component of this model, that is the weighted and bias initialization. So we have an initialized weighted and bias many times. We have performed the train many times, and we have performed reconstruction many times. And so at the end, what we have is n reconstruction, actually 100 reconstruction, because we have seen that they were stable at the end. So we had 100 reconstruction of equally probable realization, so equally probable distribution of geomaterial. And this allowed us not only to have a category in a given point, but also the probability of each category to be predicted in a given point. Here you can see an example. Of course, all the models are based on the same data, so of course they are similar. But if you can look closer, there are some differences between different reconstructions, so they're going to give us different probabilities in different points. Okay, you can see here our result. This is the geological reconstruction that provides the model category in each given point. The resolution at the end will be of 1 kilometer on the planar plane, so on the horizontal plane, and 1 meter on the vertical direction of resolution. We perform our simulation until 400 meters below the ground level. So here what you see is the probability to the model category to be predicted in a given point. So we have, for every cell, we have the probability of the category of each category to be predicted in this point, and this probability is evaluated, as I told you, as the number of reconstruction that predict category 1, for example, one category in a given point, divided the entire number of reconstruction that we have performed. We have employed the probability in order to estimate the uncertainty. We use the Shannon entropy. We use this Shannon entropy to obtain the uncertainty. Here you can see the comparison between the geological reconstruction, so the distribution of geomaterial categories, and the associated uncertainty values in each point of in each cell of the grid. This is a comparison between a local study from a local geological study that was available within the area and our reconstruction. As you can see, we are not able to catch all the details because, of course, we are working in a larger scale with respect of the detailed study, but we are able to predict the main traces. So we can see two different layers, and the red line was provided by the local study that was available in the area, and was dividing a superficial aquifer mainly based by gravel, and we were able to predict mainly gravel on the upper part of the red line. And the lower part was mainly made by clay, and we were able also to predict the lower part. It's interesting also how you can see the highest values, the highest values of uncertainty are really close to the boundary between these two aquifer systems. So at the end of this first phase, the results are we have built a three-dimensional georeference dataset that include all the lithological data that are available within the area. We have been able to do a probabilistic hydrogeological reconstruction. We have been also able to estimate the uncertainty, quantify the uncertainty of this reconstruction, and we have information that are already applicable to predict the spatial distribution of properties of hydrogeological properties within the aquifer system of the fault plane. That are going to be applying on phase 2. Phase 2 is already anticipated to you, is going to be related to the development of a methodology to perform inverse modeling in a large scale context. So the study area is going to be the same, and the two key components of these of phase 2 of the methodology are of course the groundwater flow model. That is a challenge by itself because at such large scale we have a lot of complexity, and the methodology, the technique that we have used to optimize the objective function in order to parameterize the model. So the three main objectives of this phase are: first, realize a parameterized model that's going to provide us information on groundwater flow dynamics within the fault plane. The second objective is to create a methodology that is efficient and suitable for these kind of large-scale application. And the last, inverse modeling, so for the methodology for inverse modeling this large-scale application. And the last objective is going to be related to estimate the uncertainty associated to the model, to the model input, the relative impact that uncertainty of model input has on the model output through an informed global sensitivity analysis. Okay, the study area is the same, but the groundwater flow model is going to be modeled only for the planning area. So within this black domain, you can see in the middle of the watershed, and on the lateral part, we're going to perform the on the whole domain. We're going to evaluate the groundwater charge. The three main steps of these of building up the groundwater flow model at this scale are, of course, evaluating the groundwater recharge at this scale, the setup of the boundary condition, and the estimate of the groundwater properties. In order to estimate the groundwater recharge, what we have done is to build a large-scale groundwater recharge model. We have used soil-water balance model that perform a mass balance model on each cell in which the domain has been discretized. In this case, we have discretized our domain with cell with a resolution of 250 meters per 250 meters. In each of these cells, we have performed a mass balance, as written here. The input component on each cell are the precipitation, the irrigation, and the inflow from the neighbor cells. The output of each cell is composed by the water that evapotranspirated. This is evapotranspirated. The outflow due to the runoff, and the water intercepted. We also have a last component that is related to the water stored within a cell. Okay? In order to perform these soil-water balance at this scale, we had to collect a lot of data from different data sources. We have collected data from Copernicus Climate Change Service. From this service, we have collected the data associated to the precipitation and the temperature in the whole domain. We have collected also from Copernicus the land cover model. So we have in each cell a land cover category, and we have relied on a global scale map of soil texture data in order to also have data of the soil. And finally, we have also combined, in order to estimate irrigation, we have combined the Eurocrop map. That is a map that has been based on in situ data of different cropland. So we have combined this with the Korean land cover model in order to estimate the distribution of each crop within our study area. The output of this step is the groundwater recharge, the transient groundwater recharge, a map that provides us the distribution of the groundwater recharge throughout the whole domain. And this, the code, in order to do that, has been uploaded on a GitHub repository. And all the codes are available in Jupyter Notebook, so everyone can access to the code, and the code is well described. And using this code, you can access directly to the sources. So you can access directly the Copernicus database in order to download the data for your study area, for example, and then perform and evaluate groundwater recharge to a large-scale system. The second phase of the groundwater model step is the selection, is the start of the boundary condition. So we have set a coast and depth boundary condition along the coastline. We have set an inflow condition on the rest of the lateral surface, here represented in pink. So basically what we have done, we have calculated the groundwater recharge on the mountainous area, and then we have imposed this mass of water as a boundary condition inflow on the lateral surfaces, and so this flow has been calculated using the result of the previous step. Then we have used as the last boundary condition that we have imposed is associated to the rivers. So we have taken the 20 main rivers within the domain, and we have imposed a third type boundary condition. And in order to impose this boundary condition, we're going to have to estimate this parameter C that is related to the riverbed conductance. So we're going to have 20 extra parameters to be estimated in the calibration phase. In order to assess the distribution of the property of the hydraulic conductivity specifically within the domain, what we have done has been apply the information that we have obtained in phase 1. So we have used the geological reconstruction obtained in phase 1 in order to estimate the hydraulic conductivity in each cell of the groundwater flow simulation grid. So in each cell of the flow simulation grid, we have estimated the hydraulic conductivity as a weighted sum that come from the hydraulic conductivity values of each of the six categories that we have used in phase 1, multiplied by a weight that is related to the probability that we have estimated in each cell of the geological reconstruction. Now let me talk about the inverse modeling phase. So in order to parameterize the model, we have used a unique dataset that's similar to what done for the dataset of the hydrological data. It includes the data coming from the different sources of different regions. And in order, the parameters that must be estimated are 27. 6 are related to the 6 geomaterial category that we have used that I've explained to you that we have used in phase 1. Then we have a parameter related to a correction coefficient for the lateral inflow. And we have the 20 parameters related to the riverbed conductance of each all the 20 rivers that we have modeled. In order to do so, in order to parameterize the model, we have decided to employ a differential evolution optimization algorithm. This algorithm is inspired to Darwinian evolution theory. Basically, what this algorithm does is considering a set of parameters. It considers a set of parameters as a population member. This population member is composed by parameter, and each parameter is a gene. So we have a combination of two population members, so a combination of the gene of the two population members. That means the combination of the parameters of the two population members to obtain a son members. That is going to be the combination of the parameter of the two parents set of parameters. The new set of parameters is going to be evaluated the objective function. The objective function is related to the error between the hydraulic head simulated and hydraulic head measure. So if the objective function of the son provide a lower error with respect to the parents, it will survive the parents. Otherwise, the parents will survive the son, and the son solution is going to be discarded. We are going to test different set of parameters until it converges to an optimum value of the optimization function. What about our problem? Our problem was a little more complex to apply such a simple model. So we have decided to apply a modified version that better suits for our application. And in our context, we have two kinds of parameters. The one related to the hydraulic conductivity properties, and the other related to the riverbed conductance. We have noticed that the riverbed conductance parameters mainly affect the value of the simulated hydraulic head around the riverside. So we have split our objective function into different objective functions. We have the first objective function. This is going to be related only on the first 6 parameters, the one related to the hydraulic conductivity value. And the second objective function is going to be related only to the 20 parameters related to the riverbed conductance. And it's going to use only the hydraulic head values around the riversides. In order to efficiently optimize these two objective functions, what we have done has been applied the coevolutionary differential evolution algorithm. What this coevolutionary differential evolution algorithm does, basically, it evaluates a new generation of population 1 that is associated with objective function 1, and then provide information to the population of the related to objective function 2, and then it proceed evaluating the generation 2 of objective function 2. Then the information of generation 2 of objective function 2 will be provided back to generation 2 of population 1, and we proceed in parallel optimizing the two objective functions simultaneously. After we perform the calibration with this novel technique, what we have done has been, the last part of this methodology that we present here, is to perform an informed global sensitivity analysis. We have performed a global sensitivity analysis employing the Morris indexes. These sensitivity analysis allowed us to estimate how varying the parameters around the optimal value that we have obtained will affect the output. And here you can see two different examples. We have the Morris index for the hydraulic conductivity of the sand, and with the Morris indexes, we are also able to see where this parameter affects the most the output. So as you can see here, for the hydraulic conductivity value of the sand, here these parameters is going to affect the whole domain, basically the hydraulic head simulated in the whole domain. While if you look at the riverbed conductance, for example, this is the Lampo River that passes really close to Milan. These affect mainly the area around the riverside. So the output of this second phase are here summarized. We have been able to estimate the hydraulic head throughout the whole domain. We have been able to estimate the groundwater flow dynamics with a parameterized model. We have been able to estimate the three-dimensional distribution of the hydraulic conductivity within our domain. And finally, we have been able also to assess the relative impact of uncertainty model parameters on the model output, in our case, the hydraulic head. Okay, let me conclude my presentation with the third phase, with the last phase, that is related to a little bit different topic, but is related to So it's related to a deep learning technique applied to transport of solute, to estimate solid transport of solute within a groundwater flow. So what we have done here has been build a methodology that is able to estimate early solute arrival time and preferential flow path. Let me first define what is early solute arrival time. We define early solute arrival time as the time that the first 1% of particle reach a given control plane. The first 1% of particle of a released contaminant reach the control plane. While the preferential flow path is the path that this first 1% of particle follow to reach a control plane. The main goal of this phase are to identify the location of preferential flow path using a deep convolutional neural network instead of simulating flow and transport, and estimate the early solute arrival time starting from the information that are included within the preferential flow path. In order to do so, we have generated many random hydraulic conductivity fields, starting from their statistics. So we have imposed standard deviation of hydraulic conductivity, average hydraulic conductivity, the integral scale, and we have employed these covariant models. Then for each of the fields that we have generated, we have solved the flow, groundwater flow model using a finite difference scheme. And then after that, we have solved the particle tracking code. And this way, we were able to generate the training and test dataset that we're going to use for train and test the deep learning model. After that, our question was, okay, we are able to estimate the early arrival time and preferential flow path in a regular manner, like as done before, like using flow simulation, flow and transport simulation. But is it possible to estimate the preferential flow path position without solving for transport, but using a deep learning technique? So what we have done is using a convolutional neural network in order to a convolutional neural network that usually is used for semantic segmentation for autonomous driving in order to divide the street from cars from trees. We have used that in order to divide area where we have the preferential flow path and area where we don't have preferential flow path within an image of that represents the hydraulic conductivity field. In order to do so, we have employed 3 different convolutional neural network-based models that increase their complexity. You can see here the 3 models, the scheme of the 3 models. On the top right, we have the simplest model, and on the bottom, we have the more complex model. They differ on the encoder part, so they have a different complexity encoding part. These models are usually used for categorizing images. We have adapted these models in order to perform semantic segmentation. We have performed here semantic segmentation. I present here the result for semantic segmentation of the preferential flow path for 3 different preferential flow path conditions. So we have here on the left the fields, so the input of the neural network. Then we have on the second column the preferential flow path estimating using flow and transport simulation. And then here the last 3 columns are related to the preferential flow path estimating using semantic segmentation and so convolutional neural network. You can see on the right we have the more complex model, and this is the model that provides the best performance for semantic segmentation. Now let's talk about the second step of the 3rd phase. So the idea here was, okay, can we estimate the early solute arrival time starting from the information that are within the preferential flow path? And in order to do so, what we have done has been extract the average hydraulic conductivity, the standard deviation of the hydraulic conductivity, the tortuosity, and the integral scale within the preferential flow path in order to feed a neural network model that is going to provide us as an output the early arrival time. Well, we have trained this model using some of the simulation that we have already performed with flow and transport simulation. Then we have tested the model. Here you can see the result on the test the test model. On the y-axis, there is the on the y-axis are the value obtained through the flow and transport simulation. On the x-axis, you can see the one predicted with the neural network. What you can see here, there is a good agreement between the early arrival time simulated with flow and transport and the one predicted with the neural network. And then on the right, you can see the probability distribution of the early arrival time obtained with flow and transport simulation and the one predicted with the neural network model. And you can see it's quite fairly good overlapping on them. We try also to further increase the complexity of the model. Instead of providing the integral scale, we have provided in input the whole variogram information, so the whole variogram value for all the lags, and to see if the model will improve the performance in predicting the early arrival time. What we have noticed that the performance are very similar, so we have decided to stay to the simplest model that has a much lower computational cost. After we have tested our model, we have performed a sensitivity analysis in order to understand which were the input that provide affect the most the variance of the output. So what we have noticed what we have employed is a Sobol index. So the first order Sobol index that indicates the direct impact of one input to the variance of the output, and we have noticed that the input that quantifies the highest fraction of the variance of the output is the average hydraulic conductivity of the preferential flow path. While looking at the total order that also consider the interaction between input parameters, we can see that all the model parameters affect the outputs. I will conclude my presentation with the conclusion of the third phase and the conclusion of my presentation. So the whole presentation, showing you the result. Those are the box plot of the result of the combined methodology. So we have combined the first phase that predict the preferential flow path position using deep convolutional neural network, and the second part that use neural network to exploit information of the preferential flow path in order to estimate early arrival time. We have combined these two steps in a single methodology, and here you can see the result. The result say to us that all the three models are able to estimate the average early arrival time, but the model that represents better the distribution of the early arrival time is the one associated to the more complex convolutional neural network. And this is in agreement with the result that I've shown you before, the result of the semantic segmentation. I conclude here my presentation. If you have any question about the three phases of the presentation, you can ask me your question now. Or for phase one, we already published a paper that you can reach through our website, through the Maple website. For phase two and phase three, for phase two, we have submitted the paper, so stay tuned on our website for the publication. And for phase three, we are almost there to submit also the paper for this phase. So even though if you're interested in this phase, you can stay tuned for that. And hopefully in the future, it's going to be published. So if you have any question, I'm also available.